So continuing on with our entropy and Gibbs free energy section, we're going to start looking at standard entropy today. Our learning intention will be to use standard entropies to calculate entropy change in chemical reactions. Okay, so here's just a quick recap on what we've done so far. We know that entropy is a measure of the degree of randomness or disorder or chaos of a system. The classic example we can think of here is a bedroom. If we don't put energy into creating order, it will tend towards a state of chaos or disorder, and that's what our universe is doing. It will always tend towards a state of randomness or chaos, which is high entropy. Qualitatively, entropy of liquid is greater than the entropy of a solid. Entropy of a gas is obviously greater than the entropy of a liquid or a solid. Entropy increases when a substance is broken up. Say we dissolve a solid, we just increase the number of particles and they have this random chaotic motion. So you're therefore increasing entropy or chaos or disorder. Temperature also increases entropy. Again, you're just creating more kinetic energy in those molecules. So therefore you just have a higher level of randomness in that substance or that system. That equals high entropy. Entropy generally increases in reactions in which the total number of product molecules is greater than the number of reactant molecules, except when you're producing a gas from non-gaseous substances. So just quickly to recap as well, we've got 4 scenarios over here. Let's have a look to see which ones have increasing or decreasing entropy. So a jigsaw puzzle, we take it apart and put it back in the box. So we have an increase in entropy in that case. We have a nice ordered jigsaw puzzle. We break it up into multiple pieces and create disorder. Clothes are folded away. That would decrease entropy. So we're putting some energy in there to create some order. We have a decrease in entropy. Ice to steam, so we're going from a solid to a gas. We have a massive increase in entropy there. And at the bottom here, we've got 2 solutions and we are forming 2 solids. So we are creating order. We would have a decrease in entropy in that particular equation at the bottom. So standard entropy is a value that we can put on substances to give us an indication of the level of disorder or randomness with that particular substance. The standard molar entropy, or we can just call it entropy, of a substance is the entropy or disorder of 1 mole of the substance in its standard state. Entropy has the units, joules per Kelvin per mole. Now, to calculate the standard entropy change in a chemical reaction, we're going to use this formula down the bottom. It looks pretty similar to when we calculate enthalpy. So the change in entropy, delta S, is equal to the sum of the entropy of the products minus the sum of the entropy of the reactants. So we'll get into a couple of calculations in a second, but have a look at this table over here, and we'll have a look at some of the values that we have for the entropy of these substances. So if we have a look at diamond, for instance, it's a very ordered solid state. Therefore, it has a very low 2.4 here, joules per Kelvin per mole entropy value. If we go up to water vapor, H2O gas, we have a much higher entropy value here of 188.7 joules per Kelvin per mole. Now, technically, if you have a solid at 0 Kelvin, you have a crystal structure at 0 Kelvin, you would have 0 entropy. So it does rely a lot on that temperature of the substance. What do we got? Well, look, compare here the entropy here of our gas state of water to our liquid state here. You can see that the entropy of a liquid, which makes sense from what we've done so far, the entropy of that liquid is quite low compared to its gas state. Okay, so let's go through a couple of worked examples here. Let's calculate the standard entropy change for the combustion of propane using standard entropy values in table 16.2, which is from your textbook. Standard molar entropies at 298 Kelvin, so standard temperature. All right, so just remember here, our change in entropy is going to be equal to the sum of the entropy of the products minus the sum of the entropy of the reactants. All right, so let's look at our products here. We've got a change in entropy is going to equal what have we got? 3 moles of CO2, 4 moles of water vapor. So we use our table and we look those up. And just be careful when you're looking up H2O that you are getting the gas phase, not in the liquid. So just be careful with that. If you're doing an exam and you need to extract something from a table, be very careful you're getting the correct state here. Hopefully I get the right one after saying that. So what do we got here? Our change in entropy is going to be 3 moles of CO2. So let's do 3 times. We'll have a look at CO2 and we've got 214. Plus, we need to do the sum of our products. 4 moles of water vapor, 4 times 189. Minus the sum of the entropies of our reactants. So let's have a look at our table. We've got 1 mole of propane, so 270, plus 5 moles of oxygen, so 5 times 205. All right. So we've got 1398 minus 270 plus 5 times 205, 1295. So in this reaction here, the change in standard entropy is plus 103 joules per Kelvin per mole. All right, so what's that telling us here? Well, remember, if we have a plus value, the plus delta S equals an increase in entropy. So an increase in the disorder or randomness of that particular chemical reaction. And let's have a look at it qualitatively and go back up to the formula and have a look. We've got our reactants, we've got 6 mole of gas. Everything's a gas here, so we don't have to worry about liquid, solid, gas. 6 mole versus 7. So we've increased the moles of gas. We should have an increase in entropy, and we do have an increase here. We've got plus 103 joules per Kelvin per mole. So here's our last example we'll go through, and perhaps you want to pause the video now, have a go at it, and then you can jump back in and check to see how you went. Okay, so the change in entropy, remember, is equal to the sum of the entropy of the products minus the sum of the entropy of the reactants. So we've got carbon monoxide, 3 moles of hydrogen as our products. We've got some methane and water vapor as our reactants. So let's use our table here and we'll put some values in. So the change in entropy here will be, let's have a look, 198. So we'll go for carbon monoxide, 198. Plus, then we've got 3 moles of hydrogen as our other product, 3 times 131, minus the sum of the entropy of our reactants. So we've got, what do we got here? Methane, 186, plus 1 mole of water vapor, H2O, 189. That's going to be 591 minus 375. And finally, delta S, change in entropy. In this particular reaction, we have plus 216 joules per Kelvin per mole. Now, keep in mind, this is in joules, so when we start calculating Gibbs free energy, we're going to change that to, well, we'll have to change that to kilojoules, but we can leave it at joules for the time being. So again, what's it telling us? We have a positive delta S, or positive change in entropy, which means we have an increase. We have an increase in entropy. And again, qualitatively, just have a look at the formula up the top here, and we'll see if that makes sense. So on the left, well, everything's a gas, so we don't have to worry about different states. On the left, we have 2 moles of gas, and on the right, we have 4. And that corresponds here to an increase in our entropy. That does make sense. All right, so that's how we calculate standard entropy of any particular reaction.